Here we have an example of a competition system. So we have two population of two species X and Y. You see that both equation here X and Y are logistic. So we have the term X square and Y square here. So it's limited itself. For example, we can have an upper bound for the population so that X compete with itself in its own species for the space, for the resources. And when X and Y interact, you see that when there is presence of Y, this one will be decreasing. When there is a presence of X, the population of Y will also be decreasing. So you see that is a competition system. They are competitors. Now we will look at the critical points and sketch the phase diagram for this system. For the critical points, we compute xy so that these are 0. So x3, x2y, 0. This one will give us two cases, x equal to 0 or x plus 2 times y equal to 3. And this one equal to 0. So let's look at case 1. The second equation here will give us y times 2 minus y minus x equal to 0. So we also have two cases, y 0 or x plus y equals 2. So case 1 we have critical point 0, 0. Case 2, x equal to 0. And therefore 0 plus y equal to 2. We have another critical point 0, 2. Case 3, x plus 2y is 3. Y equal to 0. In this case, y equals 0 and x equal to 3. 3, 0 is a critical point. And case 4, x plus 2y 3 and x plus y equal 2. So y equal to 3 minus 2, y equal to 1, x equal to 1. We have a critical point 1, 1. So we found 4 critical points for this case. And we have the almost linear system. We compute the Jacobian matrix. Let's call the first one is f of xy, the second one g of xy, Jacobian matrix. 3 minus 2x minus 2y minus 2 times x minus y 2y minus x. Now we have 4 critical points. So first case 0, 0. Jacobian matrix is now 3, 0, 0, 2. We have a diagonal matrix. We know for sure lambda 1 is 3, lambda 2 is 2, and this is diagonal. You know that 3 will correspond to 1, 0, 2 correspond to 0, 1. V1 1, 0, V2 0, 1. So in this case we have 2 positive eigenvalues. We have a source here. The origin is a source, and it's unstable because they are positive. Unstable. The picture we will see. Let's get that then. One 0 and 0 1, 1 1 lambda 1 equal to 3, lambda 2 equal to 2. So they both go off infinity. Now when t tends to infinity, that one will influence more. That will parallel to that when t is go big, and when t small is follow the blue. This would look like this. The other one, you have the same. The other quadrant. So I sketch it like that. Some of them. So this is the first case. The second case we have 0, 2 at the critical point 0, 2. Jacobian matrix. Now we have 0, 2, 3, minus 0, minus 4, 0, minus 2, 2, minus 4, minus 0, minus 1, 0, minus 2, minus 2. So now we have an upper triangular matrix. We know for sure lambda 1 equal to minus 1, lambda 2 equal to minus 2. In this case, you see that minus 2 here corresponds 0, 2. So the eigenvectors correspond to that will be v2, 0, 1. So that we can see immediately. So if you take this matrix, multiply 0, 1, you get the second columns, which is this vector. 2 times this vector. And about the first one, lambda 1 equal to minus 1. We need to find the eigenvectors. Minus 1 plus 1, 0, minus 2 plus 1. So 0, 0, minus 2, minus 1. So if we multiply AB, think of this as AB here, then you have minus 2A minus B, 0. So 2A equal to minus B, or B equal to minus 2A. So AB A minus 2A, A 1 minus 2, 1 minus 2, you can choose this to be the corresponding eigenvectors for the eigenvalues lambda 1. V1, 1 minus 2. Now we have the two eigenvectors values that are both negative, we have a sink. Lambda 1 corresponds to 1 minus 2. So this is our V1. So this gives us this line. And it is a sink. So both lambda is negative, so lambda 1 minus 1. V1's here. 1 minus 2. The second one, lambda equal to minus 2, 0, 1. 0, 1 is this one. So we have this vertical axis go inward the origin. So the trajectories, a few trajectory could be lambda 2 minus 2 V2 0, 1. So if t tend to infinity, positive infinity, then this one exponential e minus 2t will decay so fast compared with e minus t. So we will follow the black one here when this is big. When this is big, we follow that. And when this is negative infinity, we follow the blue one. So I just sketch the pictures would look like this. And same for the other quadrant. So this is what happens around the critical point 0, 2. Now we continue with 3, 0. Jacobian matrix, this one. 3, so 3 minus 6, 0, 2 minus 0, minus 3, minus 3, minus 6, 0, minus 1. So we have two eigenvalues. Lambda 1 is minus 3, correspond to that we know V1 will be 1, 0. The second one is minus 1. Now we need to find V2. So minus 3 minus lambda 2, so plus 1, minus 6, 0, minus 1, minus 1, so 0. Minus 2 minus 6, 0, 0. A plus 3b, 0. A minus 3b, minus 3b, b. So minus 3, 1 will be the corresponding eigenvectors. Now we can sketch the diagram. lambda 1 is 3, 1, 0. 1, 0. Lambda 1 equal to minus 3. So again, we have two negative eigenvalues. Lambda 1 minus 3, V1 here. Lambda 2 minus 1, minus 3, minus 3 and 1. So give us these vectors. And then we have this line. So again we have async. Stable. Sync. I should note that here too. Stable. Sync. Lambda 2 is minus 1 V2. So when this tend to infinity, this one exponential minus 3t decays so fast, we follow the blue one. Let's follow the blue when this is big. And the red. When it is minus infinity. Same for the other quadrant. So this is what happened near 0, 3. And the last critical point is on 1. Jacobian is 3 minus 4 minus 1 minus 2 minus 1 minus 1. So we have minus 1 minus lambda minus 2 minus 1 minus 1 minus lambda. Lambda plus 1 square minus 2 equals 0. Lambda plus 1 plus minus root 2. So we have lambda 1 minus 1 plus minus root 2. Root 2 approximates 1.414. So we have lambda 1 is approximately 0.414. Lambda 2 minus that, so we have minus 2.414. So this one we could have a saddle point because they are real of opposite side. On 1 is a saddle point. and because it's a saddle point, it is unstable. So now let's find the eigenvectors. Correspond to lambda 1 minus 1 plus root 2 minus 1 plus root 2 plus 1 minus root 2 you have minus root 2 minus 2 minus 1 minus root 2. So A, choose this one, A plus root 2 B 0. So I can choose this to be minus or A root 2 B minus 1. Root 2 minus 1 is an eigenvector correspond to V1. We can do this because we know that on the eigenspace where we have one eigenvectors, linearly independent eigenvector with correspond to lambda 1. We do similar for lambda 2. Negative 1, negative root 2. So this is a Jacobian minus lambda 2, so plus 1 plus root 2 plus 1 plus root 2 root 2 minus 2 minus 1 root 2. So you can choose V2 to be A minus A plus root 2B 0. So A you can choose to be root 2, B you can choose to be 1. Root 2, 1 is the corresponding eigenvectors correspond to that lambda 2. So we have lambda 1 and V1 here, lambda 2, V2 here. We have a saddle point. Root 2 is 1.414. Say 1.414 somewhere here. Root 2 minus 1 minus 1. So this one gives us V1. This is a line correspond to V1. Lambda 1 0 is approximately 0 or 0.4. In particular, this is positive, is go off infinity. The other one is V2 root 2 plus 1. In this case, lambda 2 negative. We have saddle point. So this is the plane x, y corresponding to the population xy. We have 0, 0 as a critical point. 1, 2, 3, 1, 2, and on. So we have 4 critical points: 0, 0, 3, 0, 0, 2, and on. Let's put on the graph here the local portrait into what we have, the big picture. One could give us this. This is 3, 0. Three, 0. So it looks like this. For 3, 0. So we should focus on the first quadrant because the population has non-negative numbers. Now let's look at this. If we start from here, so with 4 critical points, correspond to 4 equilibrium points. And then if you are not at these 4 points, you will move along the times. Yeah, so, and we just go like this. There's one light right here. This one is go toward this critical point, like this line, and we call it the separatrix. So we separate the region above and the region below. You see that if I am just in the region, let me call it region 2, and this is region 1. So region 1 is this yellow region. The region below the separatrix, when we start, for example, somewhere there in that region, over time it will bring us to here. So the population of the 2 species, it will eventually go to this critical point, so that only X survives. If we are here, for example, eventually over time, all of Y will die out, but only X survive. For the region above, for example, we are here. Eventually, over time, we will arise here. Or we are here, eventually, over time, we will get here. So in this case, you see that for this separatrix, we have 2 regions. And either way, one of the species will die out, and only one species survives. So in this case, we have the case survival of a single species. So I have a note here. For x squared and y squared terms, the coefficient here is 1 and 1. So that represents how each of them interact with themselves, like x interact with itself and y interact with itself. We say that is let's measure the inhibition. So it limits themselves by the limitation of resources environment. So this one we have, let's call it in general case B1 and B2. So the products B1 times B2 in our case the products B1 times B2 in our case 1 times 1 equal to 1 measures inhibition. So they just limit themselves without even interacting with other species. They just limit themselves. And the coefficient when we have x, y interact with each other. In this case, you see we have 2 and 1. Let me call this 2, say C1, C2 in general. We would have that. The product C1 times C2, 2 times 1, 2. This one measures the competition. And in this case, you see that C1 times C2 bigger than B1 times B2. This case, the competition is stronger than the cell limitation. And in this case, only one will survive, the other one become extinct. Survive, and the other one extinct. For the case, the self-limitation, the opposite case when we have the self-limitation bigger. Not our case though. When we have the self-limitation or inhibition bigger, the products B1 times B2 bigger than C1 times C2, inhibition bigger, then the two species can and do coexist in this case. Two species can coexist. So in our case, the competition is stronger. That's why you see that there is a separatrix there, that unless it's in this exact separatrix line, it can go into the point where they can live together. But if a small perturbation happen, it will likely it will go out from this separatrix line, and one of the species will die out, and only one can survive.